Hi, thank you so much for joining. This is Rashid here, and today we are going to look into recap of the past week. So right now we are looking into RISC-V architecture. Is RV32I that we are looking into. But before we start doing the recap, I thought it's good to look at the bigger picture of what I'm trying to build here right now. Okay, so my goal is to develop a low cost, low power, as low as I can, then RV32I is a base integer of a form of the RISC-V, and we will use only free or open source tools for this one. Okay, so it has 4 modules. So very first one is to understand RISC-V architecture or the spec of it, go in detail over the instruction set architecture of it. Exactly what we are going to build later on, because we're going to build this hardware for this one. So first we need to understand the spec. So I think because every day I bring a small video, 10-15 minutes, and I don't cover too much stuff. So and typically I ask my followers or students that, okay, you need to give me about at least 30 minutes. So 15 minutes for my video and 15 minutes to revise what I said, or maybe do some of the examples or exercises that I mentioned. Okay, so we do very small, that's why, and I have a full-time job, so I only look at this in the evening and weekends. So it's going to take me a couple of months to go over that, but that's okay. I like going a little bit slow. Okay, so a couple of months on that. Let's see how we go, if we finish it in 2 months or not, but I think I will cover it in 2 months. So, and then we will spend another 2 months on creating a hardware that implements all these instructions that we studied here. And we will use system verilog to implement that. We will do some system verilog level verification of that. Then my plan is, I forgot to mention that here I want to create a Python model of it so that it can give us practice of the instruction as well as it can help us later on during verification. Okay, so all right, after system verilog implementation, my plan is we need to validate this very thoroughly. So that eventually we have an IP that is not just a student project, but actually we can build on it an actual IP that we can distribute. Okay, so I think we will have to use some sort of very highly automated validation. So UVM, this will be new for me, so I will be learning and teaching. But I think the fact that I don't know it makes it very challenging for me. So super excited about that. It will take me, I think, 2 to 3 months because this is the first time I'm after that. Sorry for that. Somebody called me, and after that we will look into physical design for 2 to 3 months. Okay, so I will be using open source tools for that, and we will create a very low power version of a RISC-V. Okay, so that was the overall scheme of the things that what I plan to do. Okay, let's do a recap of what we covered in the last week. And by the way, the notes of this week's will be available. We'll give a link, and the quiz will be available too. Okay, so we started the week with an overview of the memory architecture. We said, okay, register file is the fastest because we have only 32 registers. Each of them is 32-bit, but we cannot, those are not enough for all the data that we need to work with. So we need a memory, right? Memory is also needed because we need to put our instructions there. So it's a headers instruction, it has data as well. All right, so the memory, I said, is okay, our program counter, which is what keeps the address of the memory, right, is 32 bits. So when it's 32 bits, how many unique locations you can access is 2 raised to power 32. So if you think of an hexadecimal, each one is 4 bits, so total we have 8. Okay, so it starts with all 0 and ends with all F. But the thing with RISC-V here is that each byte is addressable. So instead of saying that we have one address for this entire word, 32-bit, and the next 01 is for this word, we said, okay, first byte has this address, the next byte has 1, next byte is 2, next byte is 3, and the next first byte on the word 1 is actually 004. So 004, I mean the first 4 bits 4, is not only the address of this byte, but also the address if you want to pick the entire byte or the word, then that address is 4. So you can see that program counter, it increments by 4. So the last address of the word is with FFFC. I mean, of course, these are Fs. But the last byte here, the top left most, is all Fs. Understand that? Okay, so then we said, okay, we have two instructions, load word and store word, because we need to load data from the memory. And for that, we have LW load word instruction. This is the assembly instruction. Okay, and I gave an example from the book that, okay, if this instruction has, this one is the address from where we want to pull or load the data, and S7 is where we want to save that data. So we want to bring this word to, and the content of that word to after this instruction is executed will be into the register S7. Okay, this part is address generation. This is the base value, base register. 0 mean that register here which keeps all zeros, and we're adding this number. This is here is decimal. So we're adding these two, and that generates the address. The 8 is actually the address of this word too. Okay, and so we bring it and put it into 7. That is straightforward, right? So the opposite of that, now we have a data inside a register, and we want to store it on a particular location of the memory. So as you know, this store word is that instruction for that. So we want to store at this location, right? So this is decimal. Okay, don't confuse with this 14, this 20. When you convert this into hexadecimal, it becomes the address there. So this word 5, okay, so 0 plus 20, we get this address, and there we want to store the value of T3. So after this instruction is executed, the content of that location, entire word, is actually this one. Okay, so I'll look into further, okay, how to put a value into T3. Okay, then came bitwise logical instruction, and we look into AND, OR, exclusive OR. The important thing is that AND is used for clearing a certain bit within a 32-bit register, or we can say masking a certain bit. OR is used for setting a certain bit to 1 or certain number of bits to 1, or you can also say combining the two numbers, and I gave detail of that. Exclusive OR is used for inverting a certain bit. Okay, wherever 1 comes and you exclusive OR with 1, actually that input bit is inverted. Okay, and I explain all that with an example here. And this type of instruction, you can see you have source operands are to register. Destination is also register, but there is also an immediate version of those instructions. So those are called I, and I, or I exclusive are immediate ones. And the difference between these ones and these ones is that one source operand is definitely register. The other source operand is actually a number. It's a 12-bit number. Okay, and it's not value stored in register. All right, so then I gave a few examples of that. And after that, we started looking into shift instructions, where there is a shift left, there's a shift right. Both of these are logical, where zeros are fed on the part where we are feeding. His shift right is here, so we're feeding zeros here. Shift left is this one, so we're feeding zeros here. Important thing is shift right arithmetic. There is no shift left arithmetic because sign bit is here. And when we move the sign bit, when the number is arithmetic number, sign number, then instead of feeding just zeros, whatever the sign bit is, we extend that. Okay, this makes sure the number stays the same. negative, not doesn't flip the sign bit. The other important thing is shift left and shift right. When we are shifting left, we are actually multiplying that number with the power of 2. If we shift it by 2 bits, it's multiplying with 4. If with 3 bits, multiplying with 8. And shifting on the right side mean we are actually dividing it by whatever we shift. So this number 96, we shifted it right by 2. So the new number is 24. We divided it by 4. And then I gave some exercises there. What else? Yeah, just further explanation of that. What is this? Yes, this is the similarly shift left logical, shift right logical, shift right arithmetic we look into, and there are immediate versions of those as well. So this I indicates that one of them is register. This register value we want to shift left by 7, right by 17, and right arithmetic by 3, where the sign of this bit is actually replicated 3 times. Okay, then we started looking into branching. Branching makes the program more interesting because you're making some decisions, right? So whenever the decisions are made, the decisions can be based on certain conditions. So that is called conditional branching. Or the decision or the branching can be based, it's just, you have to jump anyway, and it doesn't matter what, so no condition. So this is your main tree, this is your branching off. Okay, so on the conditional we said there are 6 type of conditional branch instructions. Branch equal, branch not equal, branch less than, branch greater than or equal to, branch less than unsigned, branch greater than and equal to unsigned. The common format of these instruction is that there are 2 register values. Those values are compared according to the instruction, and if we have to make a jump to a new place, we provide a label. This eventually will be an address of another location when assembler calculates, but in assembly language we just put some letters there as a label. We look at an example here. This is where the label is. So if S0 and S1, their content is equal according to this instruction, then we jump here. Then the sequence after this instruction is here, not these ones. Okay, and then we look into branch not equal to. Yeah, that's all we covered in the last week. Hope you understood the content of those, and hopefully I explained it well. If you have any feedback, if you have any question on that, please put that in the comments and I'll follow up. All right, that's it for now. See you or talk to you in the next video. Bye.